Hello friends, welcome to engineering tutorial. So today we are going to discuss about some theoretical concepts, okay, and we'll be discussing about Gauss law and other things which will be used to calculate the electric field because of charge configurations. So before discussing Gauss law, I think we should be discussing another very important concept, which is the concept of electric flux. We have discussed about Coulomb's law, which gives us an expression related to the force existing, whether it is attractive or repulsive in nature, between two charges separated by a certain distance. Then we discussed about electric field, the force acting for unit test charge, and then we discussed various things, force due to a group of charges, electric field due to a group of charges because of different types of charge densities, linear, surface, volume, all that we discussed, superposition principle, then due to dipoles and all that. Now we'll be discussing about electric flux. Now before we discuss electric flux, we should understand the concept of area vector. Okay, area vector. So normally in a lot of discussions, even in mathematics, we treat area as a scalar quantity. But in physics, sometimes it is useful to treat area as a vector. So how we can treat area as a vector? So let us say we have any random closed surface, okay, having a certain surface area S, let's say S cube square units, whatever, meter square, centimeter square, whatever it is. So the area vector will basically be a vector, okay, whose length is directly proportional to the magnitude of the area, okay, and direction will be along the outward normal perpendicular direction. So let us say this is the area having S meter square, the magnitude. The vector will be like this, outward drawn normal, this way. This is the area vector. So generally what we do, if we have any given area, let's say any given area, we take a very small portion of it, and that is called as ds vector, and then we integrate ds to get the total area. Okay, so this ds vector is the small area element vector. It is called as the area element vector or surface area element vector. Okay, this. So this is the concept of area vector, and it is represented as n cap ds, where ds is the magnitude of the vector and n cap is the unit vector in the direction of the outward drawn normal. Okay, this. So the area vector, small area element vector, is represented as this. Okay, so suppose we have a surface like this. The vector will be like this, outward drawn normal. Suppose we have a surface like this, tilted in this fashion. The area vector will be like this. Okay, this. Outward drawn normal, away from it, directed perpendicularly away from it. Okay, this is the concept of area vector. So let us try to understand the concept of area vector with the help of some three-dimensional analysis. Let us say we have this surface here, any random surface we have taken. So if we select it entirely, this red arrow, this perpendicularly outwardly directed red arrow, this is the area vector S vector, surface area S. So here, as we rotate the surface, the in any direction in which it is tilted, it is rotated, the area vector also gets rotated along with it, like this. Okay, this is the concept of area vector. Okay, again, if we rotate it in this direction also, the area vector also rotates along with it. Okay, if it is in this direction, the area vector will point perpendicularly upwards. If it's in this direction, it will point in this direction. Then in this direction, it will point to the left. In this, it will point downwards. Then in this direction, like this, like this, like this, and it will go on and on like this. Same goes here also. For any small portion, if we select a small portion out of it, it will also rotate along with it. The small area vector, it will rotate along with it. Okay, so this is the concept of area vector. So now we'll be discussing about electric flux. So basically what electric flux is let's say we have electric field. Okay, when I have a number of electric field lines which are equally spaced, uniform electric field, we are assuming electric field intensity which is uniform, constant, and we place a surface, a two-dimensional surface, okay, in its path. Okay, this is the electric field and this is the surface, and this is the electric field. So electric flux basically is the number of electric field lines that pass through the surface, okay, that penetrate or pass through the surface area. That is called as electric flux. So electric flux is represented as phi subscript E. Okay, electric flux, which is basically the closed surface integral because the surface is closed. Okay, it should be a closed surface. Okay, closed surface integral of the dot product of the electric field vector and, as we discussed previously, the area element vector. okay, the area element vector. So suppose we have a surface like this, okay, let me bring it a bit down, okay, here. So suppose we have a surface like this, okay, this is the surface. So the surface element area vector will be like this, okay, this radially outwards, perpendicularly outward, normal. And let's say the electric field is like this, in this direction, E vector. So here this angle between the area element vector ds vector and the electric field vector theta, this becomes very important. So because E vector dot ds vector is equal to E vector modulus or magnitude ds vector modulus cosine of the angle between them. Okay, this is the representation, the mathematical representation of electric flux. Okay, this is the mathematical representation of electric flux, the dot product of the electric field and the area element vector. So if we try to understand it, okay, through a three-dimensional diagram, let's say this is the situation, this is the surface and this is the vector, the area element vector, and this red arrows, they are the electric field vector. So now if in this position, let's say this angle is theta, okay, this angle is theta, okay, this angle is theta. So now if I rotate this surface, okay, if I rotate this surface along with this area element vector, if I rotate this surface and bring it to this position, okay, in this position the angle between the area element vector and the electric field vector, that is equal to 0. In this position the angle is 0, theta is equal to 0 degree, and you can see most of the almost all the electric field lines are passing through the surface. All the electric field lines are passing through the surface. So it means that as we decrease this angle between the electric field vector and the area element vector, the electric flux increases, and at theta is equal to 0 degree, it is maximum. Surface integral of E ds cos 0 degree, because cos 0 degree is equal to 1. Okay, cos 0 degree is equal to 1. Now, if we change the situation, if we again rotate it, okay, and bring it something like this, okay, like this, in this position, okay, in this position. Here the angle between this blue vector, which is the area element vector, and the red vectors, which is the electric field vector, that is equal to 90 degree. The angle is equal to 90 degree. And as you can see, not a single electric field line is passing through the surface. Okay, not a single electric field line is passing through the surface. It means the electric flux, which is the closed surface integral of the dot product of electric field vector and the area element vector, that is equal to 0. Why? Because cos 90 degree is equal to 0. Okay, let me again try to make you understand how it happened. I'm taking it here again, and okay, I'm rotating it. So this is the particular angle. At this some electric field lines are passing. As we keep on rotating like this, the number of electric field lines that are passing through the surface, that is decreasing, and when we make it 90 degree, when this angle becomes 90 degree between the electric field vectors and the area element vectors, no electric field lines are passing through it. Okay, so if we rotate the whole system like this, you can see how it is happening. The electric field lines are passing through the surface like this. Okay, and when I rotate it completely, the surface, like this, you see all the electric field lines are passing through the surface. Again, I am repeating, this is the area element vector. Okay, in blue it is the area element vector, and these red ones are the electric field vectors. Electric field is constant, it is uniform, that's why it is equally spaced, and all the length of the electric field vectors, they are the same. Okay, so this is the thing. Okay, so here is the formula of electric flux as we have discussed previously. So here, what will be the SI unit of electric flux? So as we all know, the unit of electric field is Newton per Coulomb, and the unit SI unit of area is, let's say, meter square. So the SI unit of electric flux will be Newton meter square per Coulomb. Okay, this will be the SI unit of electric flux. And again, a very important point. So as we rotate this surface, okay, as we rotate this surface, and okay, as we rotate this surface, the number of electric field lines passing through the surface, okay, the number of electric field lines passing through the surface, it increases or decreases depending upon the angle between the area element vector ds vector and the electric field vector. As you can see, in this position, when theta is 0 degree, it is maximum, all the electric field lines are passing. As we start rotating it, see, the number of electric field lines passing through it is decreasing, again decreasing, here only 1, and now it is 0 in this position, theta is 90 degree. Then again, when we start rotating in this direction, let me shift it like this, okay, again it is increasing, okay, it is increasing, and then it will be maximum in this position. Then again it will start decreasing, it will start decreasing, then again when it becomes 270 degree or whatever, in whichever direction you want to measure, it becomes 0, then again it starts increasing, and then again 360 degree angle or 0 degree, again it is maximum. Okay, So this is the basic concept of electric flux which we have discussed. Okay.